Our goal in this course is to figure out if our elements can carry the applied loads and whether or not they'll deform too much. So in order to answer either of those questions, we first need to figure out the internal forces, which is based on statics. So we're going to remind ourselves of our statics concepts and be sure we're on the same page. When we have any sort of element, in this case this potato-like body, we want to make sure that it's in static equilibrium. So we want to look at our equations of motion in the 3D world. That is going to look like the sum of our forces in the x direction add up to 0, because we are in static, not moving equilibrium. Everything will add to 0, forces in y, forces in z, as well as our moments in those 3 dimensions as well. So that is for the 3D body. We like to live in our 2D world when we're doing analysis. It makes things easier. It tends to be what we're going to do in practice. So when we look at a simply supported beam and we have loads such that it deforms in between the supports, we want to figure out the reactions on those supports, the internal forces, so the shear and moment diagrams that you hopefully drew in statics. And when we talk about our equilibrium equations, generally we're talking about summing our forces in the x and y, where this is our x-axis. That is our y-axis, which means z is into and out of the page. So that is the axis we are bending about, which means we are using our moment about the z-axis. And typically we're talking about summing moments about a point. Go down to the 2D. These are the equations of equilibrium we take with us. So let's actually do it on this potato-like body. If I have force vectors applied, and then these 2 supports, a pin and a roller. Let's remind ourselves about the pin. It cannot translate horizontally or vertically. The roller, on the other hand, only prevents the translation. In this case, it cannot translate vertically. If we oriented the roller this way, it would prevent horizontal translation, so it just depends on how you orient it. If it's preventing something, it means that the body might want to move that way, and that support is preventing it. So there is a reaction at B in the y direction, there is a reaction at A in the y direction, and there is a reaction at A in the x direction, preventing that translation. So if I wanted to find what those forces are given the applied load F1 and F2, and then I'm going to want to use my 3 equations of equilibrium to find them. I will start writing them. I'm going to sum my forces in the x direction. My only reaction is AX, and then I have components of these force vectors. So I'm going to draw those. There's F1x, F1y. Let's call that angle theta. Let's draw our F2x and our F2y. We'll call that angle beta. So I've just broken my vector into the x and y components. I'm assuming my xy axis looks like that. So pretty standard. So I'm going to add anything in the x direction to this. I have my F1 in the x, my F2 in the x, and my RAX. My F1 is pointing negative, so it's pointing opposite of my other ones. So I'm going to write minus F1 cos theta. It's the cosine because it is adjacent to the angle I've labeled. And then minus F2 also cos because it's adjacent to the angle. And that should all add up to 0 if this body is in static equilibrium. You can also do it for the y direction. I've got RAY plus RBY, and then I have y components from both forces. Both are pointing upward, so 1 sine theta plus 2 also sine, but beta equals 0. And then I'm going to need to take the moment because I have 1 unknown, so I could solve directly for RAX. And here I have 2 unknowns, so I can't solve for both AY and BY without another equation. I have 3 unknowns total, RAX, RAY, RBY. I need all three equations of equilibrium. So I'm going to take a moment. I should choose A or B. If I choose point A, it gets rid of AY and I can calculate BY directly. If I choose point B, it gets rid of BY and I can calculate AY directly. I'm going to choose to take my moment about A, so I'm taking my moment about this point. It gets rid of AX and AY, leaves my RBY. I need to know some more geometry about this problem. I need to know this distance between the supports, so I'm going to call it L. I need to know the distance between the support, the location A, and my vector. I'm going to call that D1 vector. And I need to know the distance here, D2 vector. With that info, I should be able to write my moment equation. So I can do RBY. It's vertical, so I need this horizontal distance. So RBY times L will tell me the moment about point A. It is going counterclockwise. The easy way I think about that is go in the direction of your force and then go towards the point that you are taking a moment about. That is what your moment direction is, so in this case counterclockwise. When I go to do my other ones, this one, when I do F1x, I'm going to see counterclockwise. When I do Fy1, it's going to be clockwise. So in the direction of my force towards the point, it's to the left of it, so that will be a clockwise moment. So that is what we will see shortly. Do that component, so I'm going to take F1 in the x direction is my cos theta, and it is going to be multiplied by my D1 vector, and I need an angle for those as well. I'm going to call that one gamma, and this one phi. I want the vertical component, so that would be opposite, so this will be sine gamma. Then I have F1 sine theta, so the y component, times D1 cos gamma. So that's the moment from my F1 vector, and then I need the second one, so I'm going to take F2x. I'm going to go in the direction of the arrow towards the point, so that's clockwise. This one is up and to the left, so that's counter. So my F2 in the x direction will be a negative moment, and this one will be a positive moment about point A. I'm just doing relative, right? These two forces are just causing opposite moments, and I just want to capture that they are not causing moment in the same direction. It doesn't matter which one I call positive or negative, as long as I'm consistent. So I'm going to do minus my F2 cos beta, that was my x component. And that one I need the vertical, so D2 sine phi plus F2 sine beta D2 cos phi. All of that should add up to 0. So again, I have three equations. I have three unknowns. I can solve for them using the system of equations. It can get pretty tricky with all of our angles, but ultimately we're just breaking everything into our x and y components, adding the x together, adding the y together, making sure when we do our moment arms we are using the perpendicular distance to the force. So this is all well and good when we have determinate systems. This is primarily what we'll be dealing with in this course. We will see some indeterminacy, but all that means if we have a determinate system, just those equations of equilibrium will help us find reactions, which will lead us to our internal forces. If we have too many unknowns, we're going to get into an indeterminate system. We'll need to write additional equations, and those are going to be compatibility, which is just a fancy way of saying we are going to write information about the deflection. So we're going to need to know how to calculate deflection before we can handle indeterminate systems. Let's remind ourselves about the loads we might see on our body. We could talk about body forces, so like gravity, that acts on all body particles, typically a non-contact load, so things like weight might show up like that. We might have surface forces, so we might have a load distributed over an area, like that. So we've got that would be in pounds per square foot or pounds per square inch. You might see that written as PSI, PSF. Those are common. You might see it also written as kips per inch squared, KSI. Those are all area loads. Make sure we have a force per unit area. Metric, you might see that as Newton per meter squared or pascals. We will deal with both units. We could see that area load condensed down to a linear load or just a linear load itself. That we're going to see pounds per foot, kips per foot, or newtons per meter. Reminder, 1 kip is equal to 1,000 pounds. So it's just a conversion to, right, kip stands for kilo pound, a weird amalgamation of our metric and imperial units. So we could also have a concentrated force, and that would show up as kips, pounds, or newtons, or kilonewtons. So those are the units we're going to run into. Sometimes we like to represent our distributed or linear loads by a concentrated load. So if I see something like that, function of x, I might represent it as a concentrated force, where force equals that function acting over the length. My concentrated force would act at L over 2, right at the middle, and that's because of the centroid of this shape. If we had a different shape of our loading, so if our distributed load looked like that, my load concentrated here would look like that, and this would be at L over 3, because that's where the centroid of my triangular distribution is. So just keep that in mind. It's always in the middle when it's a uniform distributed load. If it's triangular or parabolic, we're really talking about applying it at the centroid. I can also do it with my area loads. If I look at area, and let's say I have this force acting like that. I have an area, and let's say pounds per square foot. If I want to convert that to a line load like this, then I'm going to need some dimensions. Let's call that B and that L. So if I want to go to a function of x, I need the y dimension condensed, so it would be a xy times b. And if I wanted to turn that into a point load, f would be f of x times L. So if I want to go directly from the area load, I would just multiply by the area, and that would get me to my concentrated point load at the centroid of that applied area. That's how we can kind of shift in between, and what we'll do when we talk about load paths and structures for civil engineers. We also want to remind ourselves of the reactions we might encounter in our problems. We use reactions to hold objects in static equilibrium. This is our simply supported beam. Simply supported because that's the easiest way that we can do it, and it's statically determinate. So we call that simply supported. We call this picture the cantilever. We have a vertical reaction, horizontal, and the one people like to forget, a moment reaction. This is a fixed support. This is our pin. This is our roller that we saw. Up here we have what we call an internal pin, or more commonly a hinge. And what happens at the hinge is there is no moment transferred. No moment transfer. Just axial and shear forces transfer, but it's internal because this whole thing could shift in space. So the internal pin doesn't hold it. It doesn't prevent it from translating up or down. It just prevents those two elements connected by the internal pin from moving relative to one another. So they cannot translate separately, but it is not an external pin that prevents translation. If a support prevents translation, then a force develops. So if we have a surface here, we would have a reaction force along that length. if our support prevents rotation, then we see a moment exerted. So this beam, if we load it, would want to deflect like this. It could not rotate at this fixed support. Therefore, a moment must develop to prevent that rotation. What it wants to do, if it's not prevented, is do that. So this moment is pushing it back rigid. Here we have a table from the Hibbler textbook showing what they might commonly look like. We could also have cables. There's our external pin, internal pin or hinge, fixed support roller, and a smooth support, so just being propped on a surface. We also want to make sure we feel comfortable with our free body diagrams. So if I have this potato body and I throw some supports on it with some loads, and I want to know what the reactions are or what the internal forces in the body are, then I can make a cut. We call this method of sections in statics. If this overall body is in equilibrium, then any cut I make on the body is also in equilibrium. Cut this, we are still going to see those externally applied loads that we saw, and then we will see internal forces when we cut. So we need to draw some internal forces and moments here if we cut the body. And we can do that two different ways. We could have the resultant force on the body, and we would also have a resultant moment. So the double arrow that I've drawn points in the direction of your thumb for right hand rule. So if you take your thumb, you point it in the direction of the double arrow, the way you are curling your fingers would be the resultant moment. It would look something like that. Thumb in the direction your moment is curling that way with your fingers. So you could draw it that way. You could also, probably more commonly, what we like to do is we like to know the normal force to this surface. We like to know the shear force, the force parallel to the surface, the force perpendicular to the surface, and then the bending moment. Both of those are correct representations of the internal forces. This one tends to be a little more handy of what we're going to use for design purposes and analysis of our members. So let's actually do it. So we're going to take our equilibrium equations we reminded ourselves of, we're going to take our boundary conditions, our supports, and we're going to solve for some internal forces.